to back up.
Start?
Yeah, we should start.
All right, so let me introduce our speaker. It's my pleasure to introduce Hedibert Lopes from INSPER, Brazil. Hedibert is known for his work in Bayesian analysis, and he works nicely combines applications and methodological work. So we'll hear both of those today. We'll hear some applications in financial econometrics and methodological work on Bayesian analysis. Hedibert has PhD from Duke University Statistics Department, North Carolina, not far from here. After that, spent 10 years at the University of Chicago, both School of Business, and after that, I moved to INSPER, Brazil, and now we're very happy to have you here.
Mm-hmm. Thank you, Vadim. First of all, I want to thank Vadim for being such a nice host, and first for inviting me to come here and for hosting me in his department with his family as well. And so we could continue our collaboration with Nick, who is sitting right next to you guys. This is a very old project that I've been working with these guys, since 2005. Like we started, in a particular angle, and I think now it's getting to the point where it's matured. And I want to explain through the talk why I say that. We started with an interest in modeling multivariate stochastic volatility models, meaning we wanted to model the covariance matrix of financial variables over time. So we had like 100 by 100 covariance matrix, and we wanted to model this 100 by 100 covariance matrix at every single day for like 3,000 days, 5 years, 10 years, or something like that. And when we did that, when we started thinking about that, we realized that in whatever direction you went, you would have to do, think about a 100 by 100 matrix. You have more or less in the order of, like 50,000. I can hear my own voice here. And I have more or less 50,000, coefficients that move according to a state space model, or a state space evolution equation. So then the focus of the research shifted to that. So how can we handle this high dimensional situation where many of these states, in a state space equation, many of these states are going to collapse at zero. Some of them are become a constant. Others will just navigate the space of the state on an autoregressive or some other type of dynamics. So with that change, now the title and the way we see the paper is like a parsimony inducing priors. So we're going to shrink these states in a large state space model. And that will be like one of the contributions. I think we claimed that should be the top contribution. So if I do have time, I will get to some examples. Otherwise, I'll just go to one of. There are several examples in between to build the case. But as you can see, we're going to talk a lot about the state space model, and we apply that here. So the way we present is actually the other way around with that. We approach the problem. We had this initially, and then we say, okay, we have to spend a lot of time on that. So the building block of the state equation will bring us to the large-scale state space model. So as I was just describing loosely, think about sigma t, this covariance matrix of yt, given all the information you have up to time t minus 1, like a one step ahead prediction or something like that. The thing is, this matrix, or its root, will be high dimensional. So if you have like a mean process, whatever that mean process is, it could be like a vector autoregression, it could be some regression, time invariant, it doesn't matter. What we are actually more interested in is how we model the covariance, conditional covariance of this q-dimensional vector of asset returns. So as I claimed down here, our interest is in time evolution of that matrix. So the two major difficulties are essentially, the first one is the curse of dimensionality. As I said, if Q is 100, we need Q square processes, state space equations. So everything explodes in this scenario. And secondly, and also very important, is that we have to keep this matrix positive definite. It's a covariance matrix. We wanted to use it for portfolio allocation, for other things. So it needs to be a well-behaved covariance matrix. Most of the literature up to that point, nowadays it's increasing, of course, but most of the literature would deal with up to 5 or 10, even 20 time series. So we wanted, we wanted to work and still want to work in the context where we have at least 100 time series. And the examples we have are like that. So what motivates our work is that we have high dimensional data, and we want to use state space because it's something that we're familiar with, dynamic models, and it's a very general, flexible class of models. And the way we're going to deal with the previous decimation in the previous slide, like of sigma t, will lead to parallel computing if we want. So you'll be able to break the whole covariance matrix into small pieces, univariate pieces, and then you can distribute this computation and combine it every now and then. So this is like a major advantage for the application. And as I claimed, we're going to talk a lot about priors now. Let me move straight to that. So because everything that comes later is related to these kinds of state space equations, so think about Y as any observation. It could be observable, it could be like non-observable, a state equation. It could be anything. So Y is related to S, and S is a state equation. Okay. So the way F is written there, it could be as general as possible, but you could think about the univariate stochastic volatility, an AR1 process with a measurement error where ST is the hidden state. The point is, what we want to do is to consider how we can play around with the priors, with the specification of these coefficients alpha, beta, and tau in order to accommodate different scenarios.
But F doesn't have to be linear.
No, F doesn't. So let's think about that equation in a univariate sense. So the state variable today is the state variable yesterday multiplied by beta. So you have a smooth transition, and tau governs how smooth is that transition. So that's the simplest AR1 representation for any state variable in a state space model. You could extend that to more complicated ones, but remember, we are always thinking about this as an ingredient to enter in a 50,000 dimensional problem. So any one of the 50,000 states will be driven by some function like that. So what we do, and not many people have done over the years, is that we contemplate 4 cases. And these 4 cases are very important for us, particularly dealing with the stochastic volatility of financial returns. The case 1, which is the random walk, is when the variable actually changes over time smoothly according to an AR1 process. So that is a simple case. Case 4 is similar to case 1. The difference is that you have like stationarity, which means that the smoothness is more apparent, and you can talk about long equilibrium situations. Usually, for some cases or for some problems, beta will be close to 1, which end up being pretty much like the random walk component. I'm more interested in case 2 and 3, because case 2 and 3 are the ones where we don't have a state equation. So instead of having this, suppose time is like 5,000 observations. You don't have 5,000, movements of the parameter. It's just like a constant. So instead of having a state equation, you have a constant. This is the flat line component. Because if beta is 0, alpha becomes the flat line. Or it could be that beta is 0 and alpha is 0 as well. So that component is irrelevant in my estimation. So it could be irrelevant, it could be a constant, or it could be, a AR process, stationary or non-stationary. All driven by these two parameters, alpha, beta, and then tau. So tau will be the degree of smoothness of these cases. So the traditional idea from a Bayesian point of view in state space models or in linear models like this is to try to work with a conjugate normal inverse gamma prior for alpha beta given tau square and tau square. So the joint will be like normal gamma or normal inverse gamma. But those priors are even though they lead to closed form derivations, they are very far from what we observe in reality, and very strict. So like Vadim just asked, we could have like a model that looks like this. So S is linear in the Y, or S is non-linear in Y. So in the first case is a simple local trend model with combined with the previous equation that I just showed. In the second one, we have a first order, like an SV model, like a stochastic volatility model. So ST there would be the log volatility of the return YT. So in either one of these cases, combined with that equation and those priors, that's what we want to do. The goal is to specify the prior for these components and the initial state. So here are the properties that we want to entertain. As I just mentioned, we have a prior for alpha, beta, and tau. Remember, this prior for alpha, beta, and tau is a prior for how the state variable evolves over time. So we want to contemplate these four cases, as I said, and we want tau, the variance, to be small. So we mix over these four possibilities. In our case, in the volatility scenarios, we don't care about beta being less than 0. In principle, you could make this from -1 to 1 for stationarity, but we never observe. You could even be, you could even be more strict and say that this would be 0.5 because you don't observe anything below that. But let's keep it 0 to 1. So the basic idea that we developed in this project, and it seems to be working really fine, and it extends, to a new level the way we deal with the state space models, is that we discretize lots of things because we still want to keep computation at an easy, as an important condition, fast and simple. And if you don't have conjugacy from a Bayesian point of view, you do have to use Markov chain Monte Carlo and other stuff that will be like very slow mixing. So what we do is we want to have we have beta and what is that, eta? That's like not eta, it should be tau. So beta and tau, we put like a grid on beta and tau. So let me show you a picture so we can see quickly. Let's see. I'll come back. I thought I had that picture. Oh yeah, this picture is a nice one. I'll come back. This picture should have been before. But think about this. When I have very big beta, remember beta is the autoregressive coefficient of the state equation. So when beta goes to 1, we're going from a constant state equation to something that behaves like an AR1, like a random walk. Sorry, behaves like a random walk. Well, if beta is close to 1, what I really want to do is to make alpha very small. Because as we know from unit root processes, if alpha is very big, then you're going to have like an explosive trend, like something that resembles a deterministic trend when it's not. So we don't want we don't want to entertain that possibility. So for beta close to 1, I want alpha to be more concentrated. On the other hand, if beta goes to 0, beta going to 0, what does it mean? If beta goes to 0, then the state variable is alpha plus some noise. In other words, it's a constant. And since I don't know where that constant lies, alpha, I want the prior for alpha to be as large, as spread as possible. Maybe that one coefficient in my model, which is now is not a state variable anymore, it's just like a constant. Maybe that number is like 4 instead of 0 or 2.5. So the prior here has to be, the prior for alpha, the marginal prior for alpha has to be, like, that has to contemplate beta being in these two different scenarios.
So those are confidence ellipsoids? For
Yeah,
beta?
just like a sample, yeah. This is the marginal prior for alpha and beta in the context of what I'm just going to describe back now. So the picture is nicer to see what is this joint distribution. So if you integrate out with respect to alpha here, you get that distribution. So you have like a mass, but not a point mass around 0, and another mass, not point mass, around 1. And even though this looks like 0, but it's away from 0 a little bit. Just like, okay, it could be like here or here, somewhere in between as a uniform. And that's why tau, this variance has two modes, essentially, because it's dealing pretty much with these two cases. So let me go back now. Sorry about skipping these slides. I usually don't like to do that, or I usually don't like to see that when I'm in the audience. So,
But you're not.
I'm not now, so I have the power. So here's how we sample, or how we model that variance of the state variable. So we model the variance of the state variable as a discrete grid, and we pick a few parameters. So we don't want to use the inverse gamma for this parameter, because the inverse gamma has the following problem. If you want to make the distribution far from 0, or with a fatter tail, it's going to be moving the whole density away from 0. But I don't want to move the whole density away from 0, because I want the possibility that tau is very close to 0 to make the case for a flat line. So how can I do these two things at the same time? Well, one possibility, there might be other ones, but one possibility, actually there are other ones people suggested in the literature. One possibility is to say, well, the minimum value is this one, equals to like 0.001, a very tiny one. And then you have like a probability for that one, let's say 10%. And then you split the other ones according to this exponential. So this is one idea we tried. We tried a few other ones, and that was one that worked relatively well. So in other words, instead of an inverse gamma with 2 parameters, we have a discrete distribution with 4 hyperparameters. So we have to play around with these four quantities. So the commonly used prior for tau is this inverse chi-square, the inverse gamma, and we saw that this prior is pretty hard to model in high dimension. So here you can see what's happening to these different configurations. So we're basically saying we have a prior for tau. The minimum value is pretty tiny down here, and the maximum is 0.15, and the probability of this minimum is 30%. So you put like a 30% mass at a very small number, and then the rest you just put in a decay. So that would be like, which color? Let's see. That would be the black one. The red and the blue are inverse chi-squares, inverse gamma distributions. So if you try to make this tail as fat as the other one, you're going to move the distribution here. So the chance of observing 0.005 in both of them is very minimal. It's very small. It's hard to see, but you can see that in the log density scale. So when I move to the right with the blue, you see that the tail falls much fast. With the black one, it's not that fast. And because we are now in a situation where beta, in one particular case, beta is between 0 and 1, it's much easier just to make a grid based on a Gaussian distribution in that range. That's what we do here. So the full mixture prior that we entertain are these ones. So we have a distribution for tau when beta is 1. We have the distribution for tau when beta is 0. Remember, this is driven by 4 quantities. The small value, a decaying value, the maximum, and the grid. So these are all given by that. This, and this. Beta equals 1 and beta equals 0 gives me only 2 different scenarios. So the only things that I still need to do is to think about alpha given beta equals 0, and then the distribution of beta in the interval 0, 1. So for alpha given beta, this is what we use. So if beta is equal to 0, it's a normal 0 with a big flat variance. But if beta is equal to 1, this quantity approaches 0. So that's why we get that picture I showed you later. So I'm going to skip that. Let me show you an example to hopefully illustrate what is the effect of this kind of prior setup for a state space model. Very simple state space model. Xt could be 1. I think xt in this case is just 1. So yt is st, the state variable, and the state variable follows an AR1. So this is what we would call an AR1 plus noise time series. You don't model directly the observable as an AR1, you model the unobservable latent process ST as an AR1. It's a broader class than a simple AR1. And we play around with 3 situations where beta is equal to 1, beta is equal to 0.8, and beta is equal to 0. So in this third case, we have a constant alpha of 0.5. And look at the standard deviation of the variance, or the standard deviation of the process. It's 0.01 here in this last case. And then we play around with the hyperparameters. I'm going to skip that for now, just to show you the pictures here. So, and how I read this picture is like this. In the top left is my simulated data. So the blue dots are the y's that I simulated from the red dot hidden variable. Remember, it's just like yt is xt plus noise. So, and this noise is pretty small. So, and if xt is actually an AR1, that's the behavior of the AR1. And in here, it's a mix of an AR1. It could be like a stationary process. And in here, the hidden process is just a flat process. So we feed those y's into the system, like the blue dots, and then we get this as posteriors for the parameters of interest. So in the top case, alpha was 0, and we catch alpha being 0 a posteriori as well. Beta was 1, so it's perfect because whatever prior I put on alpha, beta, and tau, for the top one, it's basically saying, well, you are right there, you give the prior weight for the AR1 higher than the other ones, and you just recover the data. So there's nothing to be too happy about, because you're saying, I simulated the data from the process, my prior is heavily weighted on that process. Of course, I recover the system. The question is what happens when you do the other way around. Like, here's my prior now, I can go back. So I'm basically saying, where is that? Here. I'm putting like 50% of my prior mass in the AR1 process, and 50% in the other 4 components of the mixture. So that's why I recover that nicely. But here, for instance, let's go to the third one so I don't waste too much time. We know that the 50% of prior that I put in the AR1 process should vanish a posteriori because the process is not an AR1, it's a flat line. So when you do that, we get a flat line, but now you see that there is a little bit of information trying to push this number to 0. Because a priori I said, well, I think this number is 0. But the data is telling me, no, that number is not 0, it's like 0.5. So there is a little tail here.
So why you have 1,000, and so you have 200 observations, and
those are like posterior draws. So I can show you those posterior processes.
So you draw many times from this process on the left, right?
Just
No,
once.
okay.
Those
So
like
okay.
MCMC draws.
So you still have 200 observations that you used to draw the posterior.
Yes, and this is basically telling me, well, I could have shown you histograms here instead of these trace plots, but I prefer the trace plots just to show you that, first of all, it's mixing relatively well, but also to show you the decay here. My posterior distribution is not going to be unbiased because my prior is not unbiased. My prior has a lot of mass in the AR1, so with only 200 observations, this is the best I can do. If I had like 2,000 observations, probably this would just go to around 0.5 and we'll all be happy. The thing is, for beta, in this case, beta is 0. But remember, I said that a priori beta is non-zero. So a posteriori, this is the posterior distribution. It's actually, trying to get away from 0. But it's not. Most of the mass is around 0. So if you draw the histogram of this trace plot, it will be like a big chunk at 0 and like a little tail. So that little tail is because the prior is too heavy on that. And the same thing for tau, for the variance.
So tau is actually means. So the red line is the true tau, right?
The red line is the yes.
And most of the mass is below this line, right?
Yeah, that's the thing. Like remember, in this case, we fixed a quantity that is like 0.005 with a certain probability, and then we have a decay that goes above like that. So it's sensitive to that quantity, of course. So if you do the histogram, probably like the middle 50 percentile will cover the true value, but I'm not too worried about that initially. I'm just showing that this will adapt whatever data you give me. Even if I use a prior that looks like that, if the data tells me different processes are being simulated, my parameters will quickly go in that direction, as opposed to the conventional conditionally conjugate priors. This example is similar, I'm just going to skip. So I'm going to go straight to where we wanted to implement this. So as I said at the beginning of my talk, our initial interest was right here. So we just flipped the other way around because we needed to solve that first. So we're sitting in this, you're sitting in this Q square problem. Like in our example, we have 94. For some reason, we don't have 100 of the S&P 100 time series. We have 94 time series, which means that we have roughly 4,500 state equations. So everything I just showed you here, I have, 5,000 of those. And of those 5,000, some of them will look like this, some of them will look like that, some of them will look like that. So I want the data to tell me.
So how did you take into account mergers and splits?
Good question.
I think that's why you have 94.
That's what I thought.
You have to ask my Taiwanese co-author.
Details.
Oh, those details are important, of course. Yes. They are definitely important. It will become even more important if you really want to use this kind of technology to model like 1,000 time series, which is what we want to do eventually. If I really want to do cloud computing, parallelization, I would be able to model 5,000 time series. But to model 5,000 time series, you not only have more series, but you also have observations starting later, finishing earlier, and then you have, there are solutions to that. For instance, adding more, hidden states, and these hidden states are like moving around, and every now and then more or less variables contribute to learn those hidden states. So this we could do with factor stochastic volatility stuff. But for now, for us, let's think about this very clean, sanitized environment where we have 95, roughly 100 time series, and I want to model this 100 by 100 covariance matrix. So what we do is, that's where the Cholesky decomposition comes in. We actually rewrite the variance covariance matrix as that decomposition, simple Cholesky decomposition, and the point is this matrix is lower triangular and its transpose is upper triangular. So what does it mean to take sigma as a product of a lower triangular, a diagonal matrix, and a lower upper triangular matrix, well, it means that if I now pre-multiply the y's, the observed asset returns, by some quantity which is lower triangular, I make this multivariate with location 0 and variance which is diagonal. So there is a transformation of the y's where the components of this transformation, they are all independent if you have Gaussianity, for instance. And the neat aspect or the neat property of this could be for many transformations, not necessarily lower triangular. The neat thing about the lower triangular is that in the first equation you have one of the variables, in the second equation you have the first one and the second one, in the third equation you have the first, the second, and the third one. So what does that entail? I'm modeling the first variable in the first equation, I'm modeling the second variable given the first variable in the second equation, and I'm modeling the third variable conditionally on the first, contemporaneous first and second in the third equation. And any single time, we're modeling one variable as a regression on the other previous variables. So, and this multiple regression is increasing number of components, but it's still univariate, univariate multiple regression. This equation here. So the price or the returns of asset I at time t, because of this decomposition, is distributed as a means of the previous I minus 1 and a variance that's time varying. So now you see that I have t everywhere. I have t in this coefficient. Oh, where's that? I don't, right? But it should be like a t here. It's here. I have a t in that coefficient. So these coefficients, they all have t, and the variance also has t. So now if you focus on that equation, forget about everything else. Think about the equation number 51. The 51st equation in my state space model, in my multivariate model, depends on 50 time series, these ones, the previous 50 asset returns, with a stochastic volatility modeling the variance. And if I don't have an index t for these coefficients, phi's, that means that we would be modeling sigma t as A without the T, HT, and A. That's what people have done in the past. They would keep this fixed because it's much simpler. It's not a state space model for A. It would be just like a multiple regression, many multiple regressions. You would do that in longitudinal studies and other things. But we want everything to be time varying. So now you can see what my problem relies. Even if I'm just talking about one of the equations, equation 50, I have 50 p's and 1 w. So I have 51 state equations, because they're all going to follow a state equation.
And you prefer ordering?
Well, that's the thing. Like ordering is an issue that we have to talk eventually. Because the ordering, in principle, mathematically, the ordering shouldn't matter, but it does because we have priors for all the things. But I'll discuss a little bit that, hopefully, soon. So let me go back here. So now this becomes a state. This becomes an observation equation in a common filter setup, where the states are these phi's and the variance. So the phi's are modeled as AR1. So now you can clearly see it where the AR1 process that we spent half of the talk talking about price for alpha, beta, and tau comes in. And the log volatilities, they also follow AR1 process. So you can see it, that I have alpha, beta, and tau for both the autoregressive state components and for the log volatilities. So that will give us Q plus 1 divided by 2 dynamic linear models. And 3 times that state is static parameters. So if you have like 5,000, as we said, we're going to have 15,000 of those coefficients. 5,000, 5,000, 5,000. So just to illustrate it once again, so everyone will be happy at least with this slide, what we see here is that if I only had 3 variables, what I'm saying is that, well, the Cholesky decomposition would produce these recursive regressions. The first equation is just like epsilon t, 1. The second equation is yt2 is equal to minus phi 2 1 t1 plus epsilon 2, and the same thing for the third one. And I'm attaching to these observational equations these 6 state equations. 3 for those phis, and then 3 for the diagonal. But of course, the diagonal is always linear in Q. So if I have 100 time series, I'm going to have 100 of those. But if I have 100 time series, I don't have only 100 of phis. I have 1 plus 2 plus 3. I have Q times Q plus 1 divided by 2. So I have way more. This model is way more populated by phis than it is by Ds. But if you are familiar with the literature in state space models, common filter, the basic common filter, for these kinds of parameters, like simple state variables or volatility ones, this is much easier to sample from than these are. So this will be like, even though it's way more parameters here, the computation will be faster here than it is for these ones. Because to efficiently sample log volatilities, you have to use some tricks, some data augmentation, mixture of Gaussians, and it takes more time to get to the results. So it will be a little bit more expensive here, even though we're going to have only 100 of those.
Just because you have this log there?
Just because I have what?
The logarithm?
Because this is not this would not be, when combined with the observation equation, this would not be a linear common filter.
Non-linear.
Linear and Gaussian. It would still be linear in the evolution equation, but it's going to be non-Gaussian. It will be log chi-square with 1 degree of freedom in the observation equation. So that log chi-square with 1 degree of freedom is replaced by a mixture of 7 or 10 Gaussians with known means, variance, and weights. And you do data augmentation there, but that is going to be costly, computationally speaking. Well, Nick is the expert sitting right there, so if he has anything to add. The expert on this, Bayesian inference in SV models. So now, from a statistical point of view, forget about state space models, forget about the priors we were talking about. What we do have is a hierarchical structure. So Bayesians like to think about modeling as hierarchical models. We have observation equations. We have the state variables in the state space model. That will be like the second stage of my hierarchical model. And I have a bunch of parameters, alpha, beta, and tau, or alpha I, beta I, tau I, alpha ij, beta ij, tau ij. Parameters, static parameters that drive the laws that govern these state variables. And we have some initial states as well. So it's pretty like complex in that sense. But the good news is that because most of the things are conditionally distributed or conditionally independent, designing an MCMC for this structure is not that complicated. So it will be like relatively straightforward to think about it. That's actually what we do. We sample the states, both the log volatilities and the recursive regression coefficients, and for sorry, we sample the log volatilities for both groups, and we sample the phis also for both groups. So we have to cycle through these quantities. As I said, this will be, remember, we had either normal distributions or a grid point for alpha, beta, and tau. So sampling these parameters will be straightforward. Sampling these parameters will also be straightforward. There will be plenty of them. Sampling these parameters, which are the state variables, this will take, the forward filter, backwards smoothing or sampling, that is well established in the Bayesian literature. And this will do the same thing for stochastic volatility models. So all the full conditionals, the steps of our MCMC are relatively well known. They were like in 2005, they're definitely well known now in 2018. So what we do is, because we have this recursive system, let me go back to that little picture. Because I have this recursive system, as you can see, I could combine the first equation with this. In the first equation, I only learn about this state. In the second equation, I learn about this one and this one. And in the third equation, I learn about these two and that one. But I could have done in three different processors. So this is what we have here. Let's see, in this picture. So this picture basically says, well, if I have more processors, the time it will take for me to run this in hours is given by that. So like if you had, this is like pretty old picture. So nowadays you can even have like 200, right? 500. It would be like very easy to do that in the clone. You take like half an hour to run for like for 100 by 100 time series. But for 100 by 100 problem with 2,500 observations, which is what we did. But the thing is, it takes 15. Is there like a mouse? You know, it takes 15 times more, 15 times longer to draw the D state than to draw the phi state, as I just mentioned to you. So what does that mean? Well, it means that when I'm starting my sampling, the first few equations, there will be like 1 coefficient phi, 2 coefficients, 3 coefficients, 4 coefficients. But to run those phi coefficients, it will be much faster than running the D coefficients. So it creates like a non-linearity of how you go down. So should you break, like if I have 100 and I have 10 processors, should I include 10 in each one? No, because the bottom part I have way more phis than Ds and then other parameters. So that's why we get this weird split, which means that if I have 100 time series and I only have 2 computers, you just include roughly like 70 equations in one, and the bottom 30 equations in the other one. Okay. So if you had like 3, then you break here. You know, all these, I don't know, like 50 something equations go to one computer from let's say 55 to 80. So like another 25 in the second computer, and then the last 20 in the third computer, something like that. Of course, as you keep moving up, you see that, you know, if you go to 20, which will be this case, even in that case, the first 20 equations will go to the first processor because it's really fast. Then you decrease to a point where it's basically at the end, every pair of equations goes to a different machine. So this tells us how this explains how, as we go down here, how we split in those 20 processors. So that was a nice picture that we had in the earlier edition of the paper. Okay. So let me show you. I guess I'm getting close to running out of time, right? We have like several examples. This one here is with 94, the whole 94 time series, and we have a few ones that are in between. So let's play around with this for 2 or 3 minutes and see if we understand how it goes. So I use 2 types of priors, or we use like several of them, but at the end we name 2 of them, what we call rougher and smoother prior. Those names are not that beautiful, but think about what would be to be a smooth prior here. Remember, like P01 is the prior mass that you put in the AR1 process. So 85% of your prior mass goes to the AR1 process. And in this case, let's see. You see that the maximum value here is 0.05 and here is 0.15. So I'm forcing this tau to be smaller in a smoother setup than it is in a non-smoother or less smoother setup. And this quantity here controls how fast this decay, like tau decays. So you see it's like 100 here, but it's 200 or 400 here. So not only this is smaller, but it goes fast to 0. So we are basically saying that in this smoother prior, the prior for tau is much more concentrated closer to 0.
So smoother means if you draw a time series from the smoother second prior, it's just going to be smoother line, right?
Yeah, much smoother line than the first one. Yeah, that's exactly what what I'm talking about. Just to give you an idea of what these two, for that system with 3 variables. So let's see what these are. This is like a prior, and this is the posterior distribution for the D state, and that's a prior, and the posterior distribution for tau for the D state as well. So on the top left, we have one of the priors. Which one is that? Now I'm confused. So let's see. Yeah, so the rougher prior is the left one, left column, and the smoother prior is the right column. So you see that the smoother prior is like heavier, you know, heavily closer to 0 when compared to that one. I mean, not too much, but there's more mass below 0.025 there than there is here. But of course, that's the prior. You combine that with the data, the posterior distribution is around 0.10 here, and it's around 0.8 in that one. It's just the effect of the prior in the 2 posterior distributions.
And data is the same.
The data is the same, of course. And the same thing here. That's for the D, like the stochastic volatility parameters, and this is for the phi. And as you can see, the phis are less sensitive to these prior choices, which is not too bad. Let's see. That picture is not. Way too many pictures here. Yeah, I think this is a second example that I prefer to show, more or less related to your question about order. So we have 9 stocks.
I was curious though, in your previous example, you included 9/11 date in that range, not this one, the previous one.
Good question. I think both of them, right?
No,
Let's see.
No, that was 2001. It was 2001.
you had, I think you did, 1997 to
Yeah.
2000.
Yeah. So I don't have here the time series themselves, but yes, there's.
So I would ask you, what would happen if you broke it, or or what do you learn
Well-
relative to things like that?
Okay. So let's see. What we have here in this picture, which I skipped, is basically what are the standard deviations. Remember, like now, because we are in a 3x3 problem, we have a 3x3 sigma t matrix. So we have 3 covariances and 3 standard deviations. So instead of covariance, I just plot the correlations. So those are the pictures of the temporal correlations of the time series over time, and those are the pictures of the standard deviations of each one of those time series. So let's pick one of them. Which one? Let's see. Let's look at del. This is the second one. So del is that second one. So you see that our model is the blue one. It's hard to see because it's pretty messed up. But how do I maximize this?
I have to go, this one, and then the left upper corner to zoom.
Ask.
You have to move mouse. This is second screen, so you have to move mouse to the second screen.
Where's the second screen? Here. I just wanted to make that middle one bigger. Yeah, just click there. Yeah, and then we can. Awesome. Just wait here because they're gonna have to move back to. So what we are doing. Forget about the red one. The red one is like we needed to compare to something that's pretty bad, that is very jittery. So you don't look at the red one. And the black one is like a standard moving average. Just take observations, compute means and variances in a window, which is non-modeling, but might be still like decent. So our model is the blue one. So around 2001, you see that these models are capturing these breaks in variances. Like, the variance is high, then it goes down, keeps going down. But more interesting is to look at the covariance, the correlations. This is new. The correlations are now. You can look at correlations. At some point, the correlations are very high. Other times they are very low, close to 0. But then it's high again, it's low again, and this measures like a financial contagion, things like that.
The middle one on the bottom, that wall
in the correlations there. That's
You mean this?
That's yeah, right where it goes up real fast. That's 9/11 there.
Yeah,
Yeah.
yeah.
Yeah, so the whole
And
market.
Everybody went
The
down.
whole market.
And there's
Whole market
a
crashes.
joint
Yeah.
movie in scariness, like the risks are high for everyone, and there's a sharing risk. So that's why the correlation that was roughly non-existing, it went to 50%.
Right.
So that's
And 98 is when the tech market crashed.
Right.
yeah. So you can. There are a few other crises in the period that you can try to mark there. I have a paper with Carlos when he was my student, Carlos Carvalho, that we do like Markov switching for these kinds of models, univariate, and we mark exactly where the crisis happened. I can show you the reference later.
It didn't cover 2008 yet.
No, it was like old. It was old. So now I go here. So the thing about the 9-dimensional example, I think I'm done, but I want to show just one picture. In the 9-dimensional example, the main reason why we did this example was to show, where's that? Oh yeah, here. Was to show that if I had flipped the series from 1 to 9 to 9 to 1, this is what we would get as standard deviations of this of some of the series. I couldn't show all of them. Mm-hmm. So here's the standard deviation of Microsoft. When I use this rougher prior, the smoother prior, or there's also a much smoother prior, which I didn't describe, but it's much smoother than that one. And as you can see, if I had done in 1 through 9 or 9 to 1, the results are very similar. You know? And it's very similar to, as well, if I looked at the IBM, or if I looked at the correlation over time of Microsoft and IBM. Out of 9, I could have picked 2 other time series to draw this picture. So the bottom line is, it doesn't answer all your questions because there are departures, so there are issues that you have to worry about. Particularly if you're serious about modeling this with 500 time series, you want to create blocks of fees that disappear. Because maybe some sectors are independent, conditionally independent of other ones. So if you want to make these priors a bit more general, creating hierarchies, then the order will start to become really important. But if you don't have any other prior information about the order, then it seems that any estimation will do because the likelihood is exchangeable. And my prior, I'm just saying, I'm just putting this prior that if I flip the indices of the prior is the same. So my posterior should not be affected that much by the prior. Unless I had an ordering implemented in the prior itself, which I don't have it. Because the likelihood is
right. But in a sense, you almost might want to estimate the prior and look at how that changed.
Well, you mean estimate the prior by, study the sensitivity of the prior.
Yeah.
Yeah, that's a good point. You should always like doubt your models and your priors, not only your priors. Your models too, because this model, we're doing like a model that is as simple as possible because we want to deal with a 100 times series. But someone would say, well, you have 9/11, you have this and that, so why don't you change the normal to a student tree distribution? Fine, it will be easy to do theoretically, but the computation will be way more expensive. So the point is, we are in a way similar to what these people in machine learning do. You want to do like something that's very big, so you have to compromise. So you're taking the models as simple as possible, the Gaussian, multivariate. The state equation is very simple as well. State, alpha plus beta state yesterday plus noise. So if you change these things, you wouldn't be able to scale to 100 or 500 or 1,000. That's it. I have a few summaries, but I don't need to talk about it. It was essentially this, trying to understand or how to change prior for parameters that are crucial to model the dynamics of static variables, and we were motivated by a situation where we would have hundreds of thousands of those.
Thank you.
If you're,
Now we'll have 3 minutes for questions.
could you in just a few words describe the basic, what am I trying to learn from this data? What do I see? How do I use it?
Oh yeah. So a few words I could show, like let's see, where's that? I thought I had a picture here.
Sorry.
This correlation. One of the outputs of things like this is to, because you have the whole covariance matrix, you can use those covariance matrix to allocate your funds in different assets using some portfolio allocation theory.
How about a specific company?
About a specific company, so these are the portfolio weights. So it could be like that the black one here is IBM. So they will say, well, this is how you should invest in IBM, or you should have invested in IBM. Each color here is a different company. That comes from the big sigma matrix. In this case, only 20, so you can visualize. But you can see that, I think I have a...
Which one's that one?
Which one is what? Good question.
I can't tell from your...
No, I cannot tell either. I don't know.
Okay, I thought maybe you knew.
No, yeah, I don't. I don't know how to make money in this scenarios. I just know how to make these models.
That's right.
But if you know someone that knows how to make money, I would definitely share my code for our fee.
Perfect.
Scott.
So for your prior for tau, you mentioned some of the limitations of the inverse gamma. I was wondering if it might help with some of those issues if you just constrain the inverse gamma instead of doing like a discretization of your prior for tau. Does that make sense?
Like constrained in which way?
Repeat the question.
Can you repeat the
So he said, like, if instead of using this this grid to parameterize the prior for tau, if I had used the inverse gamma for tau, but with some constraints, like that, instead of going from here to here, goes from here to, I don't know, like 0.5. You could do that. Computationally speaking, you would not be conjugate anymore. So, and then it would be like similar to having to run a metropolis step for all the taus.
Yeah, I was just wondering if it might have some gains.
But I mean, when I mentioned that there are other people that deal with this kind of things, some people, like recent research, what they do is they consider the standard deviation something that can be positive or negative, because what you care is the variance. In that way, the standard deviation goes to 0 on one side, the standard deviation also goes to 0 on the other side. Mm-hmm. When you take the square, they match here, so they're going to have like a big mass around 0. Mm-hmm. Again, that could be feasible, but the computation will be more costly. Of course, the next step would be to compare all these different things and see which one will be more costly or less costly nowadays in 2020. Maybe it won't be too much of a difference. Yes. But I think the main message before that is to say we're showing people here, because we learned that in the hardest way, that you cannot simply use like a conjugate prior for state space variables, because you basically eliminate the possibility of certain scenarios that you might want to entertain.
And Kalman filter is a particular case of a conjugate prior.
Yes.
And just one more follow-up on that. I mean, you had like a bimodal prior, and so did you have situations where it would get stuck in one mode and then couldn't go to the other one? I guess it depends on how much weight you put on each.
Yeah, no, good question. I don't know how to answer that question. Maybe we got stuck, but we couldn't see. No, I don't think we got stuck, because they are very. You mean the mode for beta, right?
Right.
Or for tau, because the two modes for tau are very close to one another. It's just like a construct of the way we fit the prior. A posteriori, that will be smoothed out.
Right.
But you mean the prior for beta? But remember, that's a marginal prior for beta. It's bimodal like this, but it's conditional on alpha. It's also conditional on tau. So it depends how these other parameters also interact with beta. It's a partial answer, not a complete one.